Welcome to this explainer. Look, if you've ever stared at a loading bar and felt like modern technology is hitting an absolute brick wall, you are in exactly the right place. Today, we're diving into the totally mind-bending mechanics of quantum computing. We're talking about a technology that promises to literally rewrite the rules of what a computer can fundamentally do. So let's break down this complex science together.
Here's our roadmap for today. We'll start with beyond classical computers, then get into qubits and superposition explained. After that, we'll look at today's quantum computers, the scaling challenge, and finally, Caltech's quantum legacy. Let's jump right in.
Part 1. Beyond classical computers. So why do we even need to move beyond the classical computers we use every single day? I mean, the smartphone in your pocket is an absolute marvel of engineering. Right? Well, quantum computing isn't here to replace your phone or your laptop. It's actually expected to complement them by solving problems that are, frankly, impossible for conventional computers to ever crack. It's a total game changer. We're talking about challenging our current cryptography methods, which means, yes, they could break existing security, but they'll also introduce completely new possibilities for totally private, unhackable communication. And beyond that, they'll allow us to model and manipulate other quantum systems. That opens the door to entirely new computer chips, energy technologies, next-gen sensors, and cutting-edge materials that we literally can't even dream up yet.
That brings us to Part 2, Qubits and Superposition Explained.
To understand how these machines achieve this impossible math, we really have to look at their fundamental building block, the qubit. Let's use a really simple everyday analogy here. Think of the classical bits in your current computer like an ordinary light switch. It's either completely on, representing a 1, or completely off, representing a 0. Every photo, video, and email you've ever sent is just millions of these switches pointing strictly up or down. But a quantum bit, a qubit, acts much more like a spinning coin. While it's spinning in the air, is it heads or tails? It's kind of a blur of both, right? A qubit actually processes information by existing as a 1 and a 0 simultaneously.
And that brings us to this absolutely crucial concept called superposition. Superposition is just the state where the qubit holds multiple possibilities at once. It stays in that spinning blur of 1s and 0s right up until the exact moment it stopped and measured. Just like our spinning coin finally landing flat on a table, forcing it to definitively be heads or tails, the qubit's final state isn't locked in until that measurement happens. This wild ability to process multiple possibilities at the exact same time is exactly what gives quantum computers their unimaginable speed.
Now, imagine having 2 of those spinning coins. This illustrates our next defining feature, entanglement. No matter how far apart you place these 2 spinning coins, even if one is sitting right in front of you and the other is on the complete opposite side of the planet, the very moment you slap your coin down and it lands on heads, the other coin instantly lands on heads too. Their states become mysteriously, undeniably linked together. In quantum mechanics, when the states of multiple qubits become entangled, they're linked quantum mechanically to each other. Combining this entanglement with superposition, that is what unlocks calculation capabilities totally unknown to classical computing.
But, how do you actually build a spinning coin out of pure information? To create these mind-bending qubits, scientists actually have to physically manipulate the smallest microscopic elements in the universe. We're talking about isolating actual atoms, electrically charged atoms called ions, or even single electrons. In some cases, engineers are literally printing nano-engineer artificial atoms. They create these tiny circuits of superconducting qubits using a highly advanced printing method known as lithography, which is basically like printing a microscopic photograph of a circuit.
Okay, so with all this wild talk of spinning atomic coins, teleporting information, and nanoprinting, you might genuinely be wondering, is this all just science fiction, or do these machines exist in the real world right now?
Let's look at Part 3, today's quantum computers. The truth is, they do exist right now, and the progress is absolutely fascinating. Nascent quantum computers have actually been around in various forms for over a decade. Several major tech companies have working models today. Now, the most versatile types, the ones in really fast-moving, early development that use quantum gates to control qubits, they currently operate with fewer than 100 qubits. But honestly, even at this incredibly small scale, they achieved a staggering milestone back in 2019. They successfully completed a specific calculation in just a fraction of the time a top-tier classical supercomputer would have needed. It was an incredible proof of principle that completely shocked the tech world.
But maintaining even these 100 qubits requires some extreme engineering. Because these delicate qubits are so incredibly sensitive to their surroundings, they have to be housed inside deeply nested chambers. Think of these chambers as the ultimate refrigerators, chilling the qubits down to near absolute zero. To put that into perspective for you, that is actually colder than the vacuum of deep space. This extreme cold, along with some seriously heavy shielding, is absolutely required to block out all outside magnetic and electric interference. Without it, the whole shebang just won't work.
Looking at the industry right now, there are two main approaches we need to distinguish. On one side, you have the early-stage universal quantum computers we were just talking about. These have broad potential to solve all kinds of diverse problems, but again, currently have very few qubits. On the flip side, there's a method called quantum annealing. This approach is actually further along in development and uses thousands of qubits housed in those massive cryogenic fridges. But the catch here is that quantum annealing is strictly limited to solving complex mathematical optimization problems. Companies use it right now to quickly approximate the best solutions for things like power grid scheduling, massive logistics operations, and materials discovery.
So, since the versatile universal computers have so few qubits, and the larger annealing ones are limited to very specific optimization tasks, you're probably wondering, when are general-purpose quantum computers actually going to be broadly useful for practical, everyday problems?
Which brings us to part 4, the scaling challenge.
The realistic answer? It might still be years away. Before these machines can do broadly useful work, they're going to need not just dozens, but thousands of qubits. And researchers first have to overcome some monumental scaling challenges. The biggest enemy here is a phenomenon called decoherence. You see, as you add more qubits to a system, they become increasingly harder to isolate. Remember how delicate they are? If these qubits interact with stray molecules or tiny magnetic fields in their environment, they simply collapse. They lose those fragile magical properties of superposition and entanglement. And when that happens, our spinning coin falls flat. The calculation is ruined, and the machine makes an error.
To combat this decoherence, theorists and experimentalists are aggressively inventing new strategies. The primary goal is to lengthen the time qubits can stay in their fragile quantum states, and critically, to increase the system's fault tolerance. Fault tolerance basically means preserving the accuracy of the overall calculation, even when environmental disturbances cause a few individual qubits within the system to inevitably make errors. It's essentially like building a massive safety net for the world's most delicate math problem, making sure that a single flipped coin doesn't bring down the entire system.
Part 5, Caltech's Quantum Legacy. Overcoming these massive hurdles is going to require some truly visionary science. And that brings us to the kind of pioneering research historically driven by institutions like the California Institute of Technology. Caltech researchers and alumni have quite literally been shaping this field from the very beginning. Just look at this timeline. They were forecasting quantum mechanical devices all the way back in 1959. By 1981, they were actively predicting the creation of quantum computers, and their centers heavily contributed to the scientific foundations that made that massive 2019 milestone proof of principle possible.
Their specific achievements are just staggering. Along the way, Caltech researchers performed the very first quantum teleportation experiment, proving that information could actually be transmitted over great distances. They created Shor's algorithm, a groundbreaking mathematical formula proving quantum computers could one day crack complex codes that classical computers literally cannot touch. They were the first to successfully store entangled quantum states in a memory device, and they even conceptualized the exact error correction methods we just talked about to protect that precious info from environmental noise. So, as we look at the incredible progress made from a wild theoretical idea in the 1950s to actual super-chilled nested chambers calculating at lightning speed today, we have to look forward. Think about your own life and the vast mysteries of science, medicine, and engineering. What seemingly impossible problems in medicine, space exploration, or clean energy will suddenly become easy once we finally master the delicate dance of the qubit? Thanks for joining me for this explainer, and stay curious.